Good morning, everyone. Today, we're going to learn the last programming technique you ever need. Because I think that programming is sometimes just too hard. You have to learn so many different things, like design patterns such as facades, decorators or builders, inheritance structures, complex control flows. But I like my applications as simple as possible. As simple as that. Just imagine that every dot is just some small part of your application. Maybe the first one is rendering some component, one is just processing some data, doing some networking, or getting something from your database. And all you have to do all day long is combining them together until they're large enough that you can call it an application. What usually happens after you have an application is that your requirements changes. And in that case, you just have a look at your first primitives, maybe you change some of them, recompose it together, and you have a new application removing the old one. And that is composition. And that is me. I am Thomas. I am a software engineer working for Comsystoreply. If you're ever looking for a cool job, I might be your future interviewer, and you only have to answer one question. Can you compose? And if your answer is no today, I hope we're going to change that in the next 30 minutes by following a 3-step plan. First, we're going to compose some things. Then we're going to compose all the things. And in the end, we're going to learn about the fundamentals of composition. The first thing that we're going to compose is something really old, Unix commands. They're from the 70s, and they're one of the oldest things I know that can be composed. They're small utility functions provided by your operating system, which can work, for instance, with files. And that's an example of a composed Unix commands. We're composing 3 Unix commands here. And here's an example file which we're going to use, containing some programming concepts. We pass this file to our first function, which is cat, which means concatenate and print lines. And the content of our file gets printed to the console. Right to cat, there's this pipe symbol. And this pipe symbol actually forms the composition, passing the output of cat as an input to grep. And grep is the global regular expression pattern, which removes every line that contains a small o, keeping only 4 lines left. We have one more pipe, which just does the same thing, getting the output of grep to sort, which is finally a good function name, and sorting our lines. What we did so far was we had 3 small primitives. We composed them together in order to get one more complex one. And I assume that most of you are JavaScript developers, and we can do something very similar with JavaScript. For instance, with string manipulations. And we're going to use a library called Ramda, which is a library built with composability in mind. It even has a method, which is called compose, which works very similar as the Unix pipe. We're going to compose 3 string primitives. Trim, removing some spaces, to uppercasing a string, and replace, removing a substring within a string. Thanks to compose, we can combine these 3 functions as we like, creating an uppercase trimmer, an uppercase replacer, a trimmer replacer, and an uppercase trimmer replacer. We're always replacing a lowercase a with a lowercase b. Now we can just apply the same parameters to these 4 functions. The parameter is a space, a lowercase a space, and we get our expected results. So what we just did was very similar to the first example. Once more, we had 3 small primitives. We composed them together in order to create something more complex. And it's almost the same between Unix commands and the string manipulations in JavaScript. But we can compose much more than only texts. Another thing which we can compose are components. But before I show you the example, let me first tell you a short story. I work as a software consultant. And about a year ago, my customer approached me and told me, well, Thomas, do you remember that table component we built? People had to select something in there. Well, we made a user test and no one really gets it. We probably need to replace it with something more simpler, maybe a drop-down or something. And of course, I remember the table component. Because in order to implement it, I had a long list of features. I searched through the whole internet to find that one JavaScript table library that implemented all the features. And after 2 days, I finally found it, the perfect JavaScript table framework. I integrated it, and then I noticed, well, maybe it's not that perfect. Maybe I have to change a little bit here and a little bit there. And after 2 more days, I was finally finished, integrated it. But with this change to dropdowns, I basically have to remove all my code. And that is quite a sad story, but this story could be much better if I used composition. Because with composition, every small feature of my table would be separated, and the only thing I needed to change would be the last part, which is the rendering into a table or to a dropdown. And we can do something like that with React components. I'm usually working with React. I think that an example like that should be possible with any other UI framework too. We are going to compose 2 React libraries. One is called Downshift by CanDots, and it's really a classical example of a composable library. You have a lot of small primitives, and you can build many different components out of them. The main goal of Downshift is that these components should be accessible. Here's an example of an accessible dropdown created with Downshift. It is accessible because you can control it with your keyboard, and it can be read by a screen reader. We are going to compose Downshift with React Virtualized by Brian Vaughan. React Virtualized are React components for efficiently rendering large lists and tabular data. That means if you want to render, for instance, 100,000 items into your browser, you will first have to wait for quite a long time, and then probably your browser crashes. This won't happen with React Virtualized, because with React Virtualized ensures that only the visible part of your list gets rendered to screen, and as soon as the user scrolls, these parts get switched. You can probably guess what happens when we try to compose these 2 libraries together. We get a dropdown that is able to contain multiple 100,000s of items. In code, that would look something like that. It's not important that you read the code. The only thing that I want you to see here is that we have Downshift on the outside, providing some primitives, passing it into React Virtualized, which outputs a list. So it's very similar as a Unix pipeline. And that is the working list with multiple 1,000 items. So the benefit for an application developer in writing composable code is that he can freely choose some features that he likes and easily replace them with other features. But it's not only good for application developers, it's also good for library maintainers. Because as a library maintainer, you only need to have one main concern. The maintainer of Downshift is concerned about accessibility, and the maintainer of React Virtualized is concerned about performance. And if you want them both, you just need to combine them. Let's compose the next thing. Let's compose cascading style sheets. But why would you do something like that? Imagine you're working on a huge application with multiple different pages. And there are multiple design agencies involved in styling these sites. And every morning you get a call, the design agency calls you and tells you, good morning, we created this very unique user experience with 15 different custom components. Could you add them to your style sheets? Say, of course, you add them, then the next one calls with 20 new components, and the next one, and the next one, and the next one, and finally you end up with a huge style sheet. You get some new problems. You probably shouldn't send all your style sheets to your user. And once more, composability can help you with this problem by using a composable CSS framework like Tachyons by Adam Morse. It allows you to create responsive interfaces with as little CSS as possible. But how does it work? That's a button component rendered with Tachyons, and that is the corresponding HTML. As you see, there are quite a lot of classes involved in order to render this button. Let's quickly step through them so you get an idea of how Tachyons works. You can almost see that we have here a link which is not styled at all. And then we have a blue background behind this link by adding the BG Blue class. And we add a white font by adding the class font, the white class. Next one is border radius 1. And this makes the edges a little bit rounder. This one is a multiplier. And this multiplier has some default value within tachyons. And maybe something like 6 pixels. And the multiplier 2 would have 12 pixels. 3 would have 18 pixels. And that ensures that you always use some consistent spacing if you use it, for instance, for paddings. And the consistent spacing is really important if you want to create a nice design. Next class is font size 6, making the font a little smaller. Padding horizontal 3, padding vertical 2, link removing the decorator, and dim adding a hover effect adding an opacity effect when you hover over the button. The last thing that we're gonna, the advantage of that is that your CSS basically never grows. Because if you want to create a new component, you're just reusing these small composable primitives of style sheets in order to create one. And as soon as a quite small core of tachyons is loaded into your application, you have all the CSS you need. In addition, thanks to these multipliers, it's very easy to be consistent within your design. And now the last thing which we're going to compose are graphics. And I want to do that in a live demo because I want you to see how it feels like working with composable code, because I think it's a really pleasant experience. But before we compose our code, we first decompose something, the ReactiveConf logo. And the ReactiveConf logo consists of several shapes. We have a circle in the middle, and we have a vertical ellipse here, or multiple vertical ellipses. This vertical ellipse needs to be rotated for just a little degrees, multiple times, in order to create this first ellipse group. And the next step is to rotate these ellipse groups, so by 2 times by 60 degrees to fully recreate the logo. But let's see how that looks in code and a demo. You can see my browser on the right and my editor on the left. And I wrote a little graphics library in order for this demo. It does not have that many features, but you can render some graphic elements, currently only ellipses. You can color these ellipses and rotate them. We're also using Ramda once more. And I renamed the compose method to C, so I don't have to type that much. And I'll explain these other functions as soon as we use them. Let's create our first shape, the circle. And our circle expects a radius. And we pass this radius 2 times to ellipse, because an ellipse with the same height and the same width is a circle. We want to have a white circle, so we create our first composition, composing the white fill with the circle, which is created. It's important to note that composition works from right to left and not from left to right as the Unix pipe did. Now we can render our first element, the white circle, providing it with a radius. Next step are our ellipses. Let's create a green ellipse shape. Once more, we can compose the primitives provided by the library. We have a transparent fill and a green stroke. And a stroke is just the same as a border. And of course, the ellipse. We can also pass in an array instead of only one graphical element. We provide the width and the height of the ellipse, and the first ellipse gets rendered. Now we need the rotations. So let's create some rotations by using Ramda's range method. And our range method creates an array starting by 0 with 5 elements. So we have an array of 0, 1, 2, 3, 4, 5. Oh, thank you. I think that's better. We need to map over this array. And mapping means that we apply a function to every element of this array. And we're going to apply our rotate function. Now we can create our ellipse group. And this time we need to map once more, but this time over the rotations we just created. We use the ellipse we created before. And we need to use Ramda's apply to method, because our rotations are an array of functions. And our green ellipse is an object, And apply2 flips the invocation, so it expects an object and then a function, and then applies the object to the function. Now we can pass in the ellipse group instead of our single ellipse, recreating multiple ellipses. They're not that much rotated, so let's multiply the range by a constant. And now we clearly see that there are multiple ellipses. The next step which we have to do is very similar to the previous step. Once more, we are going to rotate these ellipses. But this time, we want to rotate them by a different degree and for a different shape count. What we can just do is adding two parameters, a degree parameter and a shape count. And then we replace our constants here with these parameters. We need to reapply these old values to the rotations functions in here. And now we can rotate all of our ellipses. We're going to use Ramda's app method. And app applies an array of functions, so our rotations, with 60 degree 3 times to an array of objects, which is our ellipse group. Now we can render our ellipse group, and we recreated the ReactiveConf logo. It looks almost as beautiful as the original. And what we just did was using a lot, was really a classic example of composable code. We had some primitives that we reused, and then we were able to use the one composable library together with another one, because if two libraries are built with composability in mind, it's usually quite easy to combine them together. It was also easy to add some abstractions into our code, to reuse some functionality, and it's quite easy to move this code around. And that's what I really like about composable code. But let's get back to the slide and see what we did so far. Until this time, we composed very different things. But our actual goal is to compose all the things. So we need to find a commonality between all these parts. And the commonality is, of course, the function. Because Unix commands are functions, string manipulations are functions, components, at least React components, can be written as a function component. CSS class names are not really functions, but you can write a function that applies a class name to an element. And all these graphics primitives I showed you were functions too. What that means is that if you learn something about composing functions, you basically learn how to compose all the things. And then you can create an example like that, which is maybe a little bit contrived, but it combines almost all the things we did so far. First, we're going to call cat on a file in order to get this file from our file system. Then we use some string manipulations to transform this file into an array of strings. We pass this array of strings to React Virtualized to create a table. And for every row in the table, we are going to apply some tachyons classes. I thought about adding some ellipses to the example, but I think it's contrived enough this way. So we're just generating an index HTML out of that computation. All we have to do is call all the things with our sample text file, which is the same file from the beginning, and we get our result, a React Virtualized table built from a text file, which might be not that useful, but I think it's really cool that it's possible to compose just everything you want to if you learn about the basics of composition. But there's even one more thing. As probably all of you know, JavaScript is a language that has functions. But there are quite some other languages that has functions, like Clojure, Elm, Java, Python, Go, or any other programming language. So if you learn about function composition in general, you can reuse that for every programming language, which is especially cool if you're a JavaScript developer, because usually you learn 2 new frameworks in the morning, but this morning you're going to learn something which you can use throughout your programmer life. So the next step is to learn about the fundamentals of composition. And one part of that is pure functions. Pure functions are functions that return the same input for the same output and are free of side effects. The most easiest way to explain pure functions is by showing you an impure example. I'm going to use the library called p5.js, which is a graphics library very similar to mine, but it can do much more than just rendering ellipses, and it's a little bit faster. In order for P5 to work, it needs a draw method. This draw method gets repeatedly called for every frame P5 renders. Within this draw method, I call the rect function of P5 and a colored rect function, which is a function I wrote by myself. This function calls the fill method, which changes the color of a rectangular and then rendering a rectangular. Just by looking at this code, you might expect a result like that. But unfortunately, that's not what happens. You actually get two colored rectangulars, because the fill method had a side effect. The side effect of changing the color of every graphical element that gets rendered after fill has called. And since the draw method gets called repeatedly, every rectangular has the same color. Which is very bad for composition, because as soon as you have some side effect within your composition, you need to take care about it in all your other composition. If one of your compositions has a fill with a side effect, all the other compositions need their own fill method if they shouldn't have the same color. The more impure functions you have, the harder it gets to compose this code, and at some point, you probably lost track what your application is actually doing. So in order to stay sane, you should always try to default to pure functions and use impure functions only if you have to. Sometimes you have to.
For instance, if you want to render to a browser, it's usually an impure function. A second important fundamental of composition is immutability. Immutability means that if any parameter gets passed into your method or your function, you do not change that parameter. Instead, you create a new object. Here's the immutable version of the rotate function of my graphics library. It expects a rotation in an element, copying over all the contents of the element, and then changing only the rotation. And that is the mutable version of it. Once more, we expect a rotation in an element, but this time we're mutating the rotation of this element and returning our mutated element. If I would have used the second version for my demo, my final example would look like that, which is not really as beautiful as the ReactiveConf logo. And what happened is that I accidentally mutated every element of my example, and every ellipse in my example now has the same rotation. So once more, try to use only immutable code if you want to write really composable code, and use mutability only if you have to. Sometimes your code gets faster if you use mutability, but there are also whole programming languages built on immutability only, so it should be able to use only immutable functions. Fortunately, there's so much more to learn about composition, and since I'm such a huge fan of composition, I composed all these links together for you at this URL, so you can learn it by heart and find a lot of cool books and tutorials about the topic, and the slides, and this all the things example. Since I started today, you have 3 full days to ask me anything about composition. I'm also really interested in all these other topics. And if you want to hear a 1-hour monologue about any of them, I'm happy to help you. I started today this talk by telling you that you're going to learn the last programming technique you ever need. And I truly believe that you can build whole applications only by composing some functionalities. But it's probably not the easiest way to do so. Sometimes it gets really hard to do really composable code, and the code becomes quite complex. Even the small all the things example is quite complex under the hood. But if you want to create a truly flexible application, I think that composability is the best way to do that, and I hope that some more people will try to compose all the things from tomorrow on. Thank you.
Thomas Sojka, fantastic. So that was live coding.
Yeah.
Wow.
First time.
That was very informative. I had no idea tachyons existed outside of Star Trek. That's beautiful. Now, do we have some questions over here? It looks like we do. I'm going to read these out to you, and you're going to answer them. Firstly, what's the difference between chaining and composition?
Well, there's not that much difference. Usually chaining works from left to right, while composition works from right to left. So in Redmond there's also a pipe method, which is basically the same as compose, but just in the other direction. And so the whole part of gluing some functions together, we are chaining or composition, is only a matter of direction.
Fantastic. Do you like the answer?
Yeah, it's almost the same, I'm sorry.
Second most uploaded, why compose method is composed from right? What is the motivation behind it? It looked quite strange.
I think it's because that's the way it is done in math, where composition originated from. And usually every math function is composed from right to left. And that's why most, especially functional code, which is always sometimes quite mathy, uses compose and works from right to left. And I also didn't want to use the pipe method because otherwise my title wouldn't work, so I had to use the compose method.
Alright. Next one, is there considerable overhead to immutability, RAM for storage and CPU to copy?
There is some overhead, of course. It's not really considerable because there exists some library which help you to use immutable functions, for instance, immutable.js or Mori in JavaScript, which makes sure that if you instead of copying your whole data every time, you only copy the part that changed, and then you build up an immutable object. I think that right now at the main stage, there is a talk about a library called Immer, and it's a really cool way to do immutability, but unfortunately you cannot watch it. But you should watch it on YouTube. And it's also a third way to do immutability, which has a really low overhead on your CPU. So of course there is always some overhead. Immutability will always be faster, but if you use an immutable library, the difference shouldn't make, there's not that much difference in between them.
Alright, next question. Can we use promise for composition?
You can. Basically in the all the things example, it's not directly promise, I use something called task, which works almost as a promise. It's the only difference, or the main difference between a promise and a task is that a task is lazy. That is important because if you call a promise, it immediately starts to do whatever you want the promise to do. You do not really have a way to say to your promise, I just define my promise, and then after my definition, please start a promise, which is possible with a task. But you need that for composition because you first want to create your composition, and only at a certain point in time you want to start running through it. So you can use promises for composition, but they're called tasks, and but they have the same idea. They have the same idea as a promise. You can use them for doing some asynchronous code, and I use the task in the compose all the things example.
Fantastic. Last two questions. What text editor did you use?
Emacs, of course. The only editor in existence as far as I know.
Very passionate about it. Fantastic. Does all those composition stuff affect lifecycle of application?
I'm not sure if I understand this question correctly.
Who asked that question? Where are you? Show yourselves. Alright, next one. How do you maintain large number of pure functions? For example, do you wrap them in objects for namespace in context?
Yeah. So I think one of the cool things about composition is it is really easy to move your code around. I wouldn't necessarily wrap them usually I think it depends on the language. In a language like JavaScript, you would of course wrap that in some modules, composing multiple small primitives together that you want to reuse. But you can also wrap them objects. I don't think there's like that one answer how you want to do that, but for JavaScript I would just use modules.
Fantastic. Please give a warm round of applause to Sojka.